I first of all want to thank Dr. Lucas on giving me this wonderful opportunity. Because of this internship project, I've learned a lot in terms of personal learning and what's happening in the real world. And I also thank Chip for giving me the opportunity to work on amazing projects like this. So diving deep into what we have actually done, so I would like to share a little bit of introduction on how it started, where it started, and how it went, and what we learned through this project while working on the project. So Lucas and team like developed a model aimed at identifying various potential contributing behavioral factors to patient safety events that are occurring in operating rooms, be it surgery, radiation oncology, and various other clinical wards and perioperative areas. So there's an amazing paper written by Lucas and his team. It's a phenomenal paper. By this point of time, I've read it close to 12 to 13 times just to understand what was happening in the background. So the main focus of this particular project is this particular study utilized the team strategies and tools to enhance performance and patient safety framework. So in short, we call it team steps, along with teamwork evaluation and non-technical tool. It's called TENS instrument. So what happens generally is, so the healthcare professionals come in and anonymously report patient harm events that are happening there, and the management kind of goes over it. It's like a qualitative project where you understand where is the lapses in terms of patient safety or harm events, so that we better understand them and further on like minimize the patient safety harm events. So that's a phenomenal paper. The key findings of that paper, revealed that the most common safety behaviors contributing to patient safety events were effective communication, situational awareness, and task prioritization, while the least common behavior was appropriate instruction in certain situations. Moreover, I think process or administration issues and count discrepancies are identified as the most frequent event categories. So, just to put into the context, we had a data set that comprised of 296 de-identified patient safety event reports from a very large academic medical center. This data set was curated by generated by healthcare professionals anonymously, as well as a couple of medical students, as well as Lucas and a lot of people who worked on the project, built this data set. In a while, I'll show what are the attributes of this particular data set, and just to give a broader context of what we are doing. So you have text data given out by these healthcare professionals, and our aim was to build like a natural language processing model that can effectively classify, in terms of attributes, which is a positive one, which is a negative one. Our broader objective was to just enhance patient safety in operating rooms and perioperative areas by identifying and addressing like potential contributing behavioral factors to patient safety events. So we worked on. In a while, I'll explain a bit more about what are the attributes. But this model or this project, I particularly worked on the leadership model, capable of like accurately identifying instances of effective leadership within clinical interactions, thereby mitigating the risk of patient harm. So the model serves as a proactive approach to improving patient safety outcomes and also fostering a culture of continuous improvement within our healthcare environment. So if I move down to the data dictionary of how this particular data set looks like, you have a lot of attributes coming from, be it file ID, where did this particular harm event happen, which type of service was it, which particular hospital department was associated with the event, a general event type, a specific event type, and various other factors. But the focus of our model were two attributes. One, this attribute called B factual description. It's an additive description of the event details. So just a healthcare professional anonymously comes out and records all the information that he thinks was a harm event. So it's just a block of text for every file ID that the healthcare professional has recorded. It's all in text format. And the important attribute that helps for this classification task is the poor catch. So if you see here, this is a brief factual description, the text block that I mentioned. And we do have, we classified the data into poor catch as well as good catch. So the main four components we were looking at in terms of the TENS model was communication. That is how effectively to like healthcare professionals involved in a particular patient event were communicating. How was the leadership? Who was in charge of what, and what were their actions or responsibilities? And then the situation monitoring, as in when the event is happening, who was monitoring the situation, how actions were taking place, and how people were doing things as per the workflow. And the mutual support, how was the communication between two healthcare professionals, be it a doctor or a nurse or an MRI technician or a doctor. So that was our focus. We divided it into poor and good. So poor catch, we describe poor catch as the events that are lapses in particular attribute that I mentioned. For example, if there is a leadership issue, that goes into the poor catch. And we have subcategories called so for example, if you take communication, you have 1A, 1B, 1C, all the way until 1G. These are the different types of communication lapses that are happening there. So we didn't want to go nitty gritty and very detailed into these attributes. Our first model that we wanted to build was primarily focusing on the broader aspects, be it communication, leadership, situation monitoring, and mutual support. If you see leadership, you have 2A until 2D. And if you check out the paper by Dr. Lucas, you would find more detail on what particular 2A in terms of leadership means. But we are not going in detail because the model, particularly right now, is not built upon these, granularity of the attributes. But further down the line, when we think our model has reached very good accuracy metrics, then we would dig deeper into classifying these individual attributes as well. So anything lapses in these four attributes would go into a poor catch. Anything anything positive in terms of communication would go into the good catch, 1A until 1G. Anything good in terms of leadership would go from 2A to 2D. So this is how our particular data set was built on. And this particular model that I built since the in the last semester for my internship, only focuses on taking this brief factual description and also the poor attributes, and then kind of building a classification model that can effectively take more brief actual descriptions of the text blocks and then kind of classify them into these various attributes. When we talk about the key stakeholders, definitely Department of Human Engineering and the leadership in Department of Human Engineering, Dr. Lucas Mazur and the team are the primary stakeholders. Management at UNC Radiation Oncology and associated departments at UNC Health also benefit from such a model that can our goal is to just real time classify, or at least same day when the event occurs or somebody reports an event, we would like by the end of the day or by the start of the next day, the management has a nice visualization or Tableau dashboard or a Power BI dashboard that can say, so yesterday these were the workflows, and these were where the more harm events have happened, so that the management kind of goes and refines what they need to do in terms of quality improvement, so that they have the chance to minimize these harm events. So definitely healthcare professionals that are anonymously generating these harm events are also stakeholders. And as I mentioned, the final objective is to minimize as many patient harm events as possible. So definitely, I think patients could be definitely stakeholders in this process. So first, before using Python, I delved into various tools where we can build these models, such as NIME and Weka. But I found there were a lot of limitations in terms of using these predefined models, where adjusting the parameters could be quite cumbersome, and the results we expected did not come out. So I just quickly started working in Python to build my models. As you can see, the first step is to the raw data file that we got that we had at that point of time was a Excel file. It's a protected Excel file. You could not make any changes. So any data processing or feature engineering that you wanted to do was only on this if you can do it in Python. So I used various libraries and packages just to build this model. To name some, I used pandas from Python, NumPy, RE, TensorFlow for various models, scikit-learn, and this another package called Lime Text Explainer that kind of just gives out uh, how the model performed and what was the words that it has taken into importance and how it kind of classified. But if you, I just, this is a patch of code that shows what is happening here. This is where I just uploaded the Excel file into Google Collaboratory. That is where most part I worked on Google, in the Google Collaboratory to build these models. And you can see this is a crude form or the output of how the data set looked like. Because of the window configuration issues, I couldn't expand this, but this is just the pure format of Excel, just in Python codebook. So next important feature was data processing. If you can see, the first step was to, so our because just to play along the lines of HIPAA, I just blurred out the important data set, but I'll give you a brief description of what is happening here. So my data set, as I mentioned, consisted of good catch as well as poor catch. All the information was binary. So for example, the data set originally was handcrafted by a lot of med school students who have seen the brief factual description and then kind of classified them using the TENS framework or the TENS tool. All the information was binary. For example, I had 1As, 1Bs, 2, and so on until from 1A to 2G, from 2A to 2D. So it was binary information. If somebody thinks there is a lapse in 2A, in terms of the leadership, they would mark it as 1 because it's a poor catch. Or if there is no issue related to any leadership or communication, that whole attribute would be coded as 0. So all the information was binary there. My first job was to convert these columns to numeric integers so that I could do the aggregation, and also I had to deal with the missing values. Although the data set did not have a lot of missing values, it's just a good practice to assume if there are any non-numericals, we convert them into numericals, either zeros or ones. So this is where the aggregation goes. So for example, if you take the leadership column, I just clubbed all the 2As, 2Bs, 2C until 2D, or how many attributes there are, into kind of like a list, so that all the 4 attributes are done. So after that, I had to convert to numeric and fill NA to handle any nonce. There were no NANs. That means there was no missing data. Everything was fluid, and every attribute had values in there. So that is what I did here. So what essentially the step is, this code aggregates the processed columns into broader categories by checking if the sum of each category constituent columns is greater than 1. So for example, until from 2A to 2D, if I have all the zeros except 1, so if you add all the attributes, if it is greater than 0, then here in communication it would put as 1. So in leadership, the same. If there is 1, at least like the sum of all the attributes is greater than 0, then it would classify as 1. So that this is how I feature engineer and data process, so that I have clear columns that can depict if there is a particular issue or not. So the next step in any natural language processing model would be just text processing to clean and remove stop words. So for example, the machine understands a set of stop words in English. It's a package in Python where the stop words, although not completely, are taken away. They are given less significance in terms of the model's understanding or adaptability in terms of the classification. So just a crude example, you can see I have used here NLTK as well as stop words for this particular piece of code. For example, you have this is just a small level example of, just to show what is happening here in terms of the NLTK code. So for example, if you have a sentence called, the quick brown fox jumps over the lazy dog, after removing the stop words, the clean text would something look like this. So for example, quick, brown, fox, jumps, lazy dog. So all the stop words like the, is and all are not completely removed. They are just given less significance so that the machine can understand. These are the important words. It understands the semantic meaning, but in terms of the classification, for it to understand and classify, um, it gives less significance to them. So this is the first primary step when you are working on an NLP model. So the second important concept that comes before we run a logistic regression model is, in a moment I'll also say why we particularly use logistic regression model for such a kind of problem. So the next concept is called tokenization and padding of sequences of text data, so that we prepare it for training for the machine learning model. For example, if you see, if you have two blocks or two sentences of text such as these: the quick brown fox jumps over the lazy dog, a quick brown dog jumps over the lazy fox. We as humans understand the semantic meaning of the word, but just for the machine to understand, it kind of has to convert into particular tokens. For example, if you see the first sentence itself, the is given a token 1, quick is given a token 2, and so on and so forth. But the common word in these two in these two sentences is dog. So for example, dog is assigned a token of 8. If you see down there, so sequence 1 is this one, sequence 2 is this one. So if you see, dog is in the middle and dog is here. So whenever if you feed a corpus or a set of documents to the model, it goes and tokenizes each and every word. That's how it like passes into the logistic function, and then ultimately classify things. So tokenization is the first concept, and second is a padding sequence. So padding sequence is a concept where, for some logistic regression models or any other machine learning models, there is a uniformity in what vectors are going inside and what are the parameters. So padding sequence is just one step, before you write a CNN model or a logistic regression model. Initially, in this project, we thought it would be a wonderful idea to start with a convolutional neural network model, but in a moment I'll explain why we did not pursue the CNN model and why we stick to linear models like logistic regression function. So until this point, we removed the stop words, we tokenized everything, and we padded all the sequences for uniformity. And then the next process is to just train and split the data. So most of the predictions in logistic regression model or whatever machine learning model happens, first you train the model, you kind of understand what are the weights here, and then you test on 20% of the data. This is the split I used, 80 is to 20. So there comes the first strategy. So initially we haven't strategized anything, we just went with the flow, and I just split 80-20 training and testing. But we did not achieve the accuracy metrics that we desired for, since the data set was very balanced. We had very low instances of ones, that is anything that could be classified one. Most of the information that was there, example in these fields were, as you can just hear, you can see there are a lot of zeros but no ones. So it's kind of hard for the model to understand uh, what is happening here. So after researching and going back to the drawing book, we understood that there are several strategies where you can teach the machine, saying that you got to give more importance to the one instances, because our aim is to predict a lot of ones, that is any lapses in the leadership issues using the text block. So the first strategy we employed just to achieve our targeted accuracy statistics were, or metrics were, this strategy called rebalancing the class weights. Just to understand this little bit more, I need to give a little bit of context of what is happening in terms of logistic regression model. So any natural language processing model or any algorithm you want to build, first it starts with a concept called document a document corpus. So for example, I just gave a small example of, just to simplify the concept of NLP, so that everybody can understand better. For example, you have a corpus. Corpus is nothing but uh, a set of documents in a particular data set. So you can see I've given like various examples of different animals and phrases, and I have like 6 docs here. Completely the collection of all the 6 documents is called a corpus. And the next concept we need to understand is called term frequency. So term frequency is the total number of terms in a document, particular D. So this is a document, total number of terms in a document divided by the number of times this term D. For example, a dog appears in that particular document D. This is called term frequency. So the first concept is called term frequency, as I mentioned. So jump is the word that appears many times in the whole document corpus. So it's very common. You can see I did a color grading of anything that is blue is very common. So you have big TF scores, and anything that is red is significantly rare or less in number. You can go into the specifics of the details of examples if you want to better understand what is happening. And the second concept here I would like to discuss is called inverse document frequency. That is the total number of documents D in the whole corpus divided by the number of documents within the term appears. So TF and IDF are the two essential components somebody who's writing a natural language processing model has to understand. It's nothing but we are generating inputs for the machine learning model in terms of numericals or vectors so that it can understand very well and then classify the model. So we have two inputs that we should give to the logistic regression model. One is the TDF IDF vector. How is it calculated is using this formula called TDF IDF, where you multiply term frequency with the inverse document frequency. So if you employ this for every sequence here, then you get a set of vector called TF IDF vector, which is supposed to be one input for the logistic regression model. So you can even see high scores for brown and fox due to their rarity. So more rarer the rarer the word that appears in the document uh, is how you get high IDF. So if you have low scores for jumps because it's more common across the corpus, you have a low IDF. So that is a concept. So the next step is just developing this vector. If you originally calculate each and every words TF and IDF, you wouldn't get this number. This is just for hypothetical purposes, just to make people understand, just to display how the logistic regression generally works. So if you move on to the next concept, so yeah, we have an input vector. We calculated the TF and IDF. Now we do have an input vector here that is generated based on the inputs we give to the logistic regression model. It undergoes different phenomenon, and it there is a concept called hypothetical weights that are generated based on the input you give to the logistic regression model. And I've given a detailed explanation of what is happening here. Anything, as I mentioned, learn certain weights, and TF IDF vector corresponds to the particular weight. So just for explanation purposes, for example, hypothetical weights are 2, 3, 1 for that particular sequence. Higher positive weights indicates a stronger association with class 1. So for this example, I've taken, since most of the document corpus contained a lot of animals, my goal was to just classify this particular line or the particular animal mentioned in this string or a document is an animal. If it is an animal, we classify it as class 1. If it is not an animal, we classify it as 0. So after so logistic regressions equation goes like this: P of class 1 is equal to 1 divided by 1 plus e to the power of negative score. This is a logistic function that the under the hood, the logistic regression functions like this. It takes the two vectors, it kind of makes a byproduct, then it adds with the bias 0.5, and then the score is passed to the logistic function to map its probability between zeros and ones based on the formula. This is what happens in high level in a logistic regression model when you're working on an LLP model. If the probability comes out to be more than 0.5, so 0.5 is the threshold a lot of times a lot of models assume. So if anything, if the document's probability is more than 0.5, then we would classify it as 1. So in this example, this particular example had 0.76 for example purposes. It is classified as 1. That is the fox or the dog that is mentioned in this particular string is an animal. So these are the independent concepts. If you just purely run a logistic regression function, then you would so since there are a lot of instances that are classified as zero, you wouldn't get like targeted accuracy metrics that you hope for. So we employed a strategy which is called, as I mentioned here in the beginning, rebalancing the class weights. So what happens here is, with the class weights balance, you teach the logistic model to adjust the importance of each class based on their inverse frequency. That is, class one instances become more valuable. So you can innately teach the machine saying that yes, it is important for me that you classify ones valuable during the training, correcting for the fact that there are fewer examples of class one. That is what happened with our original data set, because it was imbalanced and we had very less positive instances, and we had to actively teach the model just saying that yes, class one is very important. So instead of 0. 0.5, the weight for a class 0 might be set lower, that is 0.5, and the weight for class 1 might be set higher, so that instinctively you are just telling the model that you raise the weight whenever you see class 1 being predicted. So everybody, I think most of the people who work on machine learning models understand these concepts of true negative, false negative, and true positive. I don't want to go into the details because it's a lecture of another time, and it takes a lot of time to just intuitively understand what is true positives and false negatives. But just for the project purposes, we wanted a high recall with a sort of 50% precision, because it is okay for the model to we wanted the model to classify as many positive events as possible rather than the negative events, because we wanted to collect like as much positive instances as possible so that we can mitigate that particular patient harm. So you can see after running the model, these were the accuracy statistics. The precision was close to 0.5, and the recall was 0.33, and the F1 score was 0.40. So just to give a brief example, what is a precision? It's a ratio between true positive predictions to the total number of positive predictions, that is true positives and false positives. If the model has high precision, it indicates that the model is reliable, very reliable in positive prediction. So if particular person is building a model and he wants to predict as many positive instances as possible, even they are like false positives, precision would help a lot. In this case, you have class 1 0.50 precision. That means when the model predicts class 1, it is correct 50% of the time. And when you come to recall is nothing but true positive predictions to the actual number of positives in the data, that is true positives plus false negatives. So any high recall indicates that the model is good at catching positive instances. So here you can see my recall is around 0.33, means that the model identified 33% of all the actual class 1 instances. So initially, when we built a convolutional neural network, the only accuracy statistic, the only metrics we focused on was accuracy, and the CNN was overfitting a lot. That's the reason we wanted to try just a linear model like logistic regression, so that it's very good at just blatantly classifying, various reports. CNNs or convolutional neural networks or any other neural networks typically tends to overfit because the data set was imbalanced for us. So it was putting more emphasis on learning or classifying as many positives as possible. And we also used various strategies in the CNN, but every time we worked more on CNN, it kind of kept getting overfitting a lot. So we thought logistic regression would be a perfect model to work in this particular case. So general interpretation of our strategy, one was the classification report suggests that the model is better at identifying instances of classes 0 compared to class 1, as indicated by higher precision, recall, and FN score for class 0. The relatively low metrics for class 1, especially recall, imply that the model struggles to identify class 1 instances correctly and often misses them, high false or negative rate. So I think there is a lot of work that can be done in this particular model too. You can do hyperparameter tuning, so that you get different accuracy statistics and a different balance between precision and recall, as well as the FN score. So this was very exciting to me when I was building the model. Once I trained the model, once all the featuring engineering and processing was done, it's now the time to take each brief factual description of the 296 rows, and then give them probabilities on what it classified. And so the first initial results were just blatant, just you can see the document ID and the predicted class. But I wanted to visualize the words, based on which words did the model classify it as a class 1 or a class 0. So then I went and worked on this package in Python called line text explanations. So this package allows us to just visualize which words accounted for both the classes. So first, upon the interesting idea given by Lucas, what we did was, uh, so a couple of medical students were very helpful. They have taken three different brief factual descriptions from the original data set, and they went through all of these. Just for security purposes, it's better me not showing the whole text block. But essentially what they did was they classified each block into these attributes, as you can see: 2a, 2b, 2c, and 2d. And also they have mentioned what was their reasoning or their belief that this particular brief factual description can be classified into certain attributes like 1a, 1b, 1e, or 1f. They did a phenomenal job in doing that. It kind of acted, this exercise acted like a blind study. We did not tell them how the model performed, or how what words it was taking into account to classify this particular brief factual description. And we kind of compared it with the model that I just built. So if you see, I want you to focus on this particular text that is highlighted, called "Blaming the Circulating Scrub." This is what the medical students have given to us in the blind study. It's just a piece of this area of the photo. Now if you see how the machine predicted it, you can see. So all the words that are in blue uh, account or classify to the class 0, and all the positives were in orange. So based off of these words, I even have a graph showing which words those are, and what are the weights of that particular words when we put it into the regression function. As you can see, the circulating scrub was in positive. So circulating scrub, the machine interpreted saying that yes, this block of text has circulating scrub. That's the reason why I'm classifying the whole this particular text block into one, that is a lapses with the leadership issue. For example, if you can see, blaming the circulating scrub is what the human has presented, and the machine kind of understood that, yeah, so the word circulating scrub was mentioned in this particular document. That's why I want to give it a high probability and classify it as a positive instance in terms of the leadership. If you go to the next set of words, although in the negatives you don't see any leadership attribute. So I forgot to mention that our first primary focus was to start with the leadership model, the leadership attributes, all the 2a until 2d. So most of the emphasis here would be on the leadership. Although here you can't see any leadership lapses, but it's an interesting case. So I mentioned poor catch as well as good catch. So poor catch is nothing but negative. It's just I just need to put a poor there rather than negative. And for the positive, it's a good catch. So you can see two words here, case and set, are in the 2b. That means this is attributing to a positive impact in terms of the leadership. So, but if you see here, we have various instances saying set and case that are all blue. That means they are pointing towards the negative. That means the positive in terms of the leadership. These words are present. That's why it's not attributing it as class 1. So it's a very interesting phenomenon that happens, opposite. So this is even interesting to just understand this concept, and that is why this I just presented this text block. So it shows how amazing the interpretations between a human as well as a machine can be when you have the right parameters and right attributes and the right kind of data with you in terms of building these machine learning models. And the third example is I want you to focus on 2C, that is a leadership. This thing called surgery slash anesthesia team. So if you go there, in the positives, you see pharmacy mentioned a lot of times here. And the model gave pharmacy a lot of weight so that it predicted it to be a positive instance. So this directly doesn't relate, but you can understand the fact that a miscommunication or any leadership lapses between pharmacy as well as surgery anesthesia teams could have might have happened there. That's the reason the model has predicted it to be a positive class, and this was very fascinating. This is one strategy. Now if you move on, there's a second strategy we wanted to pursue and see how the model would build upon that. It's the same vectorization TDF IDF scores, and then you pass it to the logistic regression function. Earlier I mentioned that the basic threshold for a machine learning model is 0. 0.5. If any probability occurs more than 0. 0.5, then it classifies as 1. But we have an option of adjusting this threshold as well. So from 0. 0.5, I adjusted the threshold to be 0.3. So any probability more than 0.3, it would classify it as 1, and any probability less than threshold, it classifies as 0. Just because we have an imbalanced data set, our main goal was to teach the model into giving an importance of how you can classify. You have to take into consideration once just to understand and predict. So these are the some like the metrics. It's the same. Close to recall was 0.90. That was a fantastic job because we adjusted the threshold. Now it's able to recall a lot of positive instances. That's why the recall increased to 0.90, and the precision is also 0.40. It is closely in lines with what we wanted to do, but I believe that a lot of work can be done just to improve these metrics as well. So I've given a detailed description of what is happening and the explanation of other metrics that were presented here. But if you come to the results haven't changed. It was the same, blaming the circulating. You can see circulating and room scrub have been detected by the model multiple times. And here also the case and set, you can also see that case and set were very important for the model. That's why it predicted as a negative instance rather than a positive instance. And it's also the same here. Pharmacy multiple times is mentioned here. So this was the second strategy, and then we understood that even though employing a lot of strategies like this in terms of fine tuning our logistic regression model, we hit a plateau in terms of the max power of a logistic regression model, and then we decided on uh, various strategies that I'll mention forward. What we're going to do, with these models and what we understood. So just for the example purposes, I've taken the whole document and given a ranking of what words it used to classify as top positive features and negative features. You can say X-ray count, missing, needle, closing, incorrect, skin. These all attributed to positive weights, as you can see. And anything with the initial patient set, came, caught, fly, left, or words like these are negative features, and they steer the model away from classifying it to positives. So what was the outcome of the entire internship or this project that I worked on? Is that the outcome of the internship was to find like a better way to standardize the way data was collected using this information. The first step we were thinking in lines or Dr. Lucas's vision was to standardize the way data was collected. We wanted information on how the model pursues particular words so that it gives us better leverage on the field when the healthcare professional is trying to, record or collect patient event harms, so that we have a more wonderful data set that we can analyze and build these dashboards quickly. So for better classification and minimization of harmful events, as we plan to work on broader range of data including clinical notes, radiographs, etc., in the upcoming project, Dr. Lucas has been funded a grant where they are deploying large scale AI models not only in the text format but also in the X-rays radiological formats, and it's a wonderful project. And I'm very glad that my work could somehow you know, uh, allow as a baseline for people who are working more on the project to understand how these linear models work, and any standardized ways of recording the data. So the data set gave us the estimation of how well an authentically collected data set performs when it's subject to various statistical analysis and algorithms in the purview of NLP and text mining, and have gained like valuable insights that will be beneficial for the broader scope of data as we plan to analyze in the upcoming projects. uh, as I mentioned multiple times, so a small and imbalanced data set was kind of like a limitation, but it's a very good learning experience, because I'm sure that Dr. Lucas and the team has abundance of data out there that can be used to train these models on a large scale basis. But we have the important learning with the smaller imbalanced data set was there are even hyperparameter tuning features that available for the logistic regression or any other machine learning models, where you can tweak them and make them understand the value of classifying positive instances or negative instances. So I wouldn't consider this as a limitation or a barrier, but it was a new learning experience. So when it comes to the next steps, we plan to employ various standardized data collection methodologies that I mentioned in the field on the board to standardize the way we develop our data sets, which will be subjected to various linear classification models or advanced models like BERT, or even the up and coming large language models, so that we can even develop interfaces for the healthcare professionals to collect this data in a particular format. Like for example, any positives would go into one box in a particular website, or all the negatives can go into another box. We are just in talks with how to standardize the data collection process. We also understood the potential of various linear models and associate techniques like the one I mentioned, rebalancing class weights, to achieve our desired accuracy metrics for the type of data we collected. And the Department of Human Engineering is also planned to work on a broader grant funded project that I just mentioned, with a wide scope of data collected and yet to be collected in the UNC Radiation Oncology and the associated UNC health departments, using the current project as a basis for devising a data strategy moving forward. And as we move forward, we also like to run similar models slash experiments on the other attributes that I mentioned, because I was primarily working on that leadership model. On the other attributes such as communication, situation monitoring, and situational awareness, even though I ran a couple of logistic regressions there, but their results for each attribute was entirely different. So we need different strategies for different models, both for the poor cats as well as good cats. So I think I would be working more forward in terms of these attributes, and develop the model further. Thank you so much.